Good afternoon, everybody.
Hello.
Yeah, good afternoon. Good afternoon, Stefano.
Yeah.
Yeah. So we'll start maybe another 2 minutes with a brief introduction. Yeah.
Okay.
Yeah. Good afternoon, everybody. Respected Honorable Vice Chancellor of the University, officers of the university, and my dear fellow participants, and also my dear all the members who have joined in the afternoon session for 10 days webinar on role of nanotechnology in food and agriculture. We're going to start the second session in the afternoon session. So by Stefano Preto. So he is AP Research Italy. He is a manager director for the AP Research. So I wanted to share a brief introduction or brief biodata of the Stefano. So Stefano born in 1965 at Italy. So basically he did his diploma in Master Scientifica, degree in physics, and he completed his dissertation title on nucleation process induced by titanium in lithium fluoride single crystal. So he is a director of research and development of EP Research, co-founder of the company also. So he has developed several hardware and softwares for the AFM, that is atomic force microscopy, which we are going to know in a short while. So he is a joint researcher at TASC laboratory of INF Trieste, Italy. So he is basically a full-time researcher, I can say, full-time researcher, especially on the biological application of scanning probe microscopy. And he got a fellowship of TASC laboratory of INFM Trieste, and he is a co-founder company of AP Research. Then he is a fellowship got CNR ICMAT to work at the circular polarization beamline of Elytra synchrotron radiation source, one of the topmost best synchrotron in the world, and fellowship at TSC laboratory of INFM Trieste. He employed so many research scholars in his institute, and he has a degree in physics from the University of Parma, and is basically is having a professional skills of atomic force microscopy. It's related to the magnetic force microscopy and electric force microscopy and Kelvin probe force microscopy, and also a conducting atomic force microscopy, local anodic oxidation, and others. Scanning near field optical microscopy for material science and biological application. And also he is having experience in scanning tunnel microscopy ASTM and ambient and UHV with related to spectroscopies and spectroscopic techniques UV, infrared, photoluminescence, Raman, and X-ray photoelectron spectroscopy XPS, and vacuum apparatus like project and maintenance of UHV vacuum systems and related microscopies and spectroscopy. And he is having a computational skills related to the Pascal, C, Visual Basic, MATLAB, Origin, image analysis, and others office softwares. And he knows office softwares like LaTeX, Microsoft Office, OpenOffice, and more than else. So he has having a more than 20 publications in the international scientific journals, and also he has presented 40 oral and poster presentation in international scientific conferences, and he has given so many speeches for seminars in the university and research laboratories, and especially in the nanotechnology related microscopies. And with his busy schedule, Stefano today has readily accepted for this our 10-day seminar for giving a talk on basically AFM applications in the field of nanotechnology. And now with us Stefano Prato from Italy. I heartily welcome to Stefano for this 10 days webinar for this presentation. May I request Stefano, please, for this session?
Yeah, thank you for a very nice introduction. Yeah, and I'm not so used to, like I think everybody in this period to give speech just in front of a PC, but I'll try to do my best. And if someone want to share their face, maybe not all the time, but while to while, just so the impression that someone is is with me. I'm not alone. So bye everybody. Thank you for being here today. And so this is also anyway a good opportunity. Yeah, just to to interact with people also without traveling too much. Okay. Some people is, I'm also in holiday, so, you know, it's not office. So, so my speech will be a little bit about FM. So it's difficult for me now to understand how many of you and how much, sorry. And well, how deep you are into the FM techniques and so on. So my talk will be a little bit more on the application of the SNOM, but not and FM. Okay, scanning probe microscope in general. I'm not going too much into detail of how the physics works, because maybe some of you already knows, some of you maybe is not physics diploma, so I'm not going to physics formula. Okay, I just want to give you a picture with some application that during my career I touched so many different fields that I want to give you the flavor of what is possible to do with the FM and with the SNOM. Okay, now I need to share my screen. Try. Share. Okay. Can you see the screen on your?
Yeah. Thank you.
Okay.
Perfect.
Nice.
Perfect. Perfect.
Okay. As a by introduction, I'm a researcher working in a private company, even though the company is located just next to the Italian synchrotron radiation source. So we are, as you read in the name, we are a research company. So we do research by ourselves, and we implement this research into products. Okay, so we do both. We do research and we also sell products. Okay, so today I'm not going to focus about products, but more on the research side that we did. Okay, so this is the logo of my company, and this is some of the instruments that is possible to. So we have an FM, a SNOM, and STM. So this family, atomic force microscope, and scanning near field optical microscopes and scanning tunneling microscope. All this family is a family of instrument that is also named also scanning probe microscopy, because you have a probe that is approaching the sample and it is measuring some physical properties of the surface. And is a scanning probe because this probe is approached to the sample and then is moved toward the surface to reconstruct a 3D mapping of your surface, plus getting some other peculiar properties of your sample and your material. So I'm working since more than 20 years on this field, and as a company, we also made many of these instruments. We are located, as I said, we were founded in 1999. So we are a quite old company in the field. We are not very big because we are, anyway, medium company, I would say. We are located here is a Trieste. I don't know, just to give you a location. We are here. There is a. Can you see the mouse moving?
Yes, Preto. Yes.
Okay. So around this mouse here it is Venice, maybe. Okay. So we are just in the corner of Italy. Okay. We are next to the border of Slovenia. You have been in Trieste, so. And we are more or less in the center of Europe, okay? And Trieste is a town where science is very important. We have, I think that a lot of professors from India visited ICTP, that is the International Center for Theoretical Physics, and we have a lot of visitors coming from all developing countries, what used to be developing country, because this ICTP was founded in 1960 by UN. So it's a UN institution, and we are visiting professors from all over the world. Okay. So this is the family of scanning probe. Maybe I want to talk a little bit. Yes, this is the location where we are. It's a very nice location. So this is on top you have our campus that is in the middle of the bushes, and this ring here is the synchronous radiation source, and our office is located just nearby. On the back side you see the Adriatic Sea. Okay, we are a few kilometers from the coast, and we have a good collaboration and relationship with the Trieste University and other research institutes that we have around there. Okay, this is just a quick overview of what where I live and what I do. Okay, now we go a little bit more in detail about AFM. Okay, just I will show you a little bit what is the possibility of FM in general, and then I will skip to another presentation that will be a little bit more focused on a biological application. Okay, that is maybe more relevant to you. But just to give you a few points, when you talk about some instrument, there are some key points that you have to take in mind. Okay. So one thing that you expect from the instruments is the resolution. Okay, so I will quote some points about resolution later on. Okay, then another point that is sometimes a little bit forgotten by the researchers is a more some parameter that is more familiar to engineers is the accuracy, because you can measure something, you need very high resolution to watch small things, but if you want to measure and to have some quantitative parameter, then accuracy becomes a relevant parameter. Another, when you have an instrument, this is in general, and I will show you what is the impact on atomic force microscopes, is the sensitivity, okay? Because the resolution is just tell you, it's like in a photo, no? You can have a lot of megapixel in your mobile phone, no? But if the sensitivity is poor, then maybe you are not able to shoot photos by night, or if there is too much of sun and so on. So sensitivity is a critical parameter. And then I will show some around the FM. There are a lot of possible collateral measurement that you can perform. I will give you an overview about that. In particular about the SNOM, then I will go to the biological application. Okay. Okay, so this is an FM. If you, for the few of you that maybe never saw an FM, this is one of the FM that we have in the lab. So we have a stage, so-called stage. The machine is quite small, is about this size. And this is the core of the movement. So the core of the machine is to move the sample in a nanoscale, okay? So every movement that we do is not done with a motor, but is done with a piezo. And we can achieve a movement that goes from some microns down to some nanometers, even less to femtometer. Okay, so this is the key, is around this part. The top part is about the sensitivity part, is where you have the cantilever of the FM. So we have the cantilever that is approaching the surface. This is our probe. Okay, so we were saying that we have scanning probe microscope. In atomic force microscope, we have the probe is a cantilever. It is approaching the sample and is, let's say, touching the sample. And okay, and then we show you what it come out. So sensitivity part is around this area here. Then we have a top view system that is a kind of link between the macro world and the nano world. No, so nano world is very, very small. So you cannot just jump into the nano world from millimeters to nanometers. So this camera allows you to downsize from the millimeter to the micrometer scale, and then with the FM you go from the micrometer to the nanometer. I will show you some later on some of this idea of application. Okay, since we are moving, let's say you have to think of a nanometer is like a few atoms. Okay, so if you want to be sure that what we measure is around the size of a few atoms, so you have to be very careful of your environment. Okay, so normally this is the core of the machine, but the machine come out with a little bit more complex system that ensure you that no contamination is going through your like acoustic noise, vibration noise, all the kind of noise. You have to preserve your instruments by external perturbation. Okay. Okay. As I said, I'm not maybe going too much into those details. If some of you want to have some specific question, I will just show you, because with FM, what you can achieve is the topography. But then you have a lot of other collateral images that you can see. I will maybe, in the example, I will show you some of them. So go back to the first task that we say resolution, okay? What it means resolution? What resolution can you achieve with the FM? So first of all, I want to stress that there are two kinds of resolution. One is the lateral resolution. So when it's like watching a video, how big is a pixel? So lateral resolution is one important parameter. The other important parameter is the Z resolution, because with FM, what you can get is a three-dimensional map like those one. Okay. Okay. You have maybe you can see here. This is a 3D map. Okay. So what you get with the scanning probe microscope in general is a map that is made by X, Y, and Z parameter. Okay, is a real, let's say, three-dimensional reconstruction of your sample. In this case, we have a carbon nanotube deposited on a highly oriented pyrolytic graphite. Okay, so these and these, those are the same images. This is a 3D view, and this is a top view. In the top view, all images that I will show you are top view images, where the bright spots represent a tall structure. Okay, you can see it here. So when it's darker means that it's a lower, and when it's brighter is a taller. Okay, so it's not a contrast, it's a real color. It's just a topography. Okay, take in mind this one in all the images that I show you. For example, if you take a cross section along this line, this is what you get. Okay, so a single wall carbon nanotube is something very, very small. Okay, you can see here this bar is 50 nanometers. Okay, so it's not a very easy task to watch this small nanotube. First of all, what you need is the Z resolution. Okay, as you see here along this profile, if you measure it here, this is around 2-3 nanometers tall. Okay, so if you measure from here to here, the size of this tube is around 3 nanometers. So it's quite shallow. Okay, and with FM you can really measure this 8 with a very nice accuracy. Okay, just yeah, I don't know. Maybe if up to now, if someone has doubt, is it clear enough?
Yeah, Preto, you can go ahead.
Okay, okay. Yeah, because I don't know if I'm going to be too technical or maybe I'm losing too much of time. Okay, I try. Okay, so this is a single wall carbon nanotube. This is an example of very nice resolution. As I said, the first argument we're talking about will be about resolution. So resolution is, first of all, lateral resolution. This image is 150 by 150 nanometers inside. So it is very, very small, okay? So this will be about the X and Y resolution, but another parameter is the Z resolution. Z resolution also is when you do a cross section, what is the smaller size that you can measure. Okay, this is an example. This is one of the few examples that I have about agriculture application. Okay, so this is a nano fertilizer. So this is some molecule that contains iron. This is iron made in a small nanoparticle. That is the aim of this group was to study what is the medium size of this nanofertilizer. Okay, what we did with FM, we deposited this was in solution, so we put a drop of this solution over a sample that in this case was again highly oriented pyrolytic graphite. So it's a piece of graphite that is very flat, is atomically flat, I would say. And then we let the solvent to evaporate, and we saw the particle that were left behind on top of the surface. Okay, this top part is a zoom of this part here. You can see the long lines, those are stripes that belongs to the substrate, to the graphite. On top you have those islands. Okay, those islands are quite nice. They are more or less around the same size. You can see it here. And they are 1.5 nanometers tall. Okay, so those are not spheric, but it's like small terraces, are a little bit hexagonal in shape. It means that they should have some kind of internal organization, and they're quite flat. It's like small terraces. Okay, and this is with FM is very important to it's not so easy to solve those one. First of all, because of the resolution, because those particles are quite small. Okay, with other techniques, it's not so easy to watch them. For example, if you use an electron microscope, you will bombard them with electrons. So what you will get is that you will eat up those molecules that will blow away and evaporate. Okay, so for some of the material, mainly for organic material, it's very important to have the resolution, but I will talk later about the sensitivity. In this case, is a non-contact, is so-called non-contact FM. So we are not touching the surface. This is very important. So this will preserve the material to be degraded. Okay, so it's one of the few methods that will allow you to watch in the nanoscale without touching really your sample. No, because with the X-ray you will bombard with the X-ray. With the scanning electron microscope we will bombard with electrons. In this case, we do not touch the surface. So we have a very a picture of a very pristine sample. Okay, so this was about the resolution. Okay, this is a peculiarity of our FM that you can perform images that goes from 100 micron by 100 micron down to very small, let's say few nanometers by few nanometers scan size. Okay. Resolution. So, as I said, those two systems, they are quite. This is 1.5 nanometers tall. This is 3 nanometers tall. That is very small. But what is the limit that you can achieve? No. So if we zoom, now we move to a solid state sample. This is a gallium arsenide where you have some atomic steps. Okay. So here you see a series of steps, crystal, okay? So you have around 10 terraces here, and each terraces, from one terrace, you can see the profile here, from one terrace to another, you have an atomic layer. It means 2.5 Armstrong or 0.24 nanometer, okay? So you can imagine that around here you have the size of one atom. So this is the one of the best Z resolution that we could prove with our instrument, and this is very good, I would say. If you zoom on these terraces, you can even measure something. This is some ondulation because this crystal, when it's exposed to air, get oxidized. So the oxide is not like atomically flat, but is a little bit waving. Okay, if we measure this wave, will be about 40 picometer, 40 picometer. It means 0.04 nanometer. Is less than 1 atom diameter. This is the kind of resolution that an FM, in particular our FM, I would say, not all the FM can achieve this kind of resolution, But this is the Z resolution that we can achieve. That is quite amazing if you think also some other technique. Okay, it's clear that even with the TEM, you can have a very nice lateral resolution, but the Z resolution is not as good as the FM. Okay, so this was to introduce you to the concept of what is usually is the main parameter that you can ask to an FM is the resolution. So to conclude, to summarize, I try to show you. I didn't talk about the numbers because numbers has been. I gave you some example of what is the X and Y and Z resolution that you can expect from FM. Now we go to the next argument that is about accuracy. Accuracy is another relevant parameter. And in our system, I just give you an example why is so useful. As I show you in FM, you can want to merge the microscopic world with a nanometer scale. Okay, so if you watch this image here, this is the optical image that you can see with our on top of FM. You remember we have a camera, an optical system. This is what you see with the optical system. The substrate is silicon in this case, and then there are some microstructure made by gold. Okay, so this is with a mask. You know, in this normal lithography system, you can say paint your substrate with many wires made of gold that goes to the central part where you have, in this case, you create some nano contacts. Okay. This is very useful if you want to develop, for example, nano sensors. Maybe in agriculture, no, is quite popular now to have microsensors, nano sensors, and to detect peculiar, maybe contamination or concentration of system. So if you are in the field of building nanosensor, then you can use a sample like this. Where you have very narrow lines here. Those lines, you can watch them by optical microscope. But if you go to the center, you will see that the color is not yellow anymore. No, the colors vanish. But it shouldn't, because the material is the same. It's gold all over the sides. But what happened here? Here it happened that those wires become so small that they are smaller than the diffraction limit. So it's not possible to watch them anymore by optical microscope. In this case, we switch to the atomic force microscope, okay? So this central area here is what you see here. So this is an optical image, and this is the zoom done with the center, done with the FM, okay? This is quite, in this case, is a very large image. This is 100 by 100 micron. Okay, it's very large. So it's one of the largest that you can get with our instrument, for example. So what is here is again some contact. As you see here in the center, you have some gaps here. This is the 3D IFM image acquired here in this area. So this size is 100 by 100 micron, and this is 200 by 200 nanometer. So this gap here is around 200 nanometer, okay? So with FM, you can really zoom down this size, as I show you here. This first, so you watch first the sample with the optical microscope, then you do a large area with FM, then you do a little bit small area, and then you zoom down to, this is 400 by 400 nanometer size. This is the same image in a 3D mapping. So if you put some molecule in the middle of here, you can measure some electrical property, for example, if you want to develop some nanosensor and so on. But okay, this is more general, depending on the research field application. What is important for the FM is that if you have this image and you want to zoom it exactly here, you need accuracy. It's not anymore a matter of resolution, okay? But you need accuracy, because if you're not accurate, maybe you tell to the system, okay, zoom this area, but the system is going to another area, because we are really in the nanoscale. So any small thermal fluctuation, any small vibration can change your mission. Your mission is to target this spot. So accuracy is an important parameter to manage with artificial 3D structures that maybe you can create in your lab. Okay, what is the advantage of having at the same time a good accuracy and a good resolution? Okay, this is another example. We can start from this image. This again a single wall carbon nanotube obtained with a non-contact FM. So this image here is exactly this image here. This is in grayscale, this is in color scale. So this is the starting point of single wall carbon nanotube that you see here. Okay, those are monatomic steps on graphite. Okay, so if I don't know if you can see very nicely, but the carbon nanotube is very, very, very long. You see, all this. Can you follow my mouse? I hope you is going and is finishing here. So this carbon nanotube is, as I showed you before, is between 2 and 3 nanometer in height, but is very, very long. Is 40 micron long. So the ratio between length and height is more than 1000. So it's not very easy to have a system that can, at the same time, can perform a very long range image like this one, and having at the same time a good resolution. For example, if your FM, some FM provide different scanner for different resolution, okay? This is not good, because during the measurement you cannot mount a high resolution scanner, because otherwise you don't see the Z, but having large area scanner, so it's not possible to mix some. So this is a limitation that we, with our experience, we try to overcome, and we propose this solution in our instrument where you can change the resolution and accuracy of the system depends on your needs on your experiment. So this is a very tough image to obtain, such a long single wall carbon nanotube in one shot. Okay, now we move to the next topics that will be about sensitivity. Okay, a good, okay, there are a lot of FM around, so it's sometimes a little bit difficult for people to understand what is the difference between each other. With numbers is different. I will try to give you some example. What is the meaning of the sensitivity? Sensitivity means that you should watch very small stuff, okay, without perturbating your sample. Because if you, during the measure, you change your sample, what you measure is not what you want to see. So sensitivity is very important, related also with resolution. For example, this is a single strain DNA molecule on top of a mica sample. Okay, so this molecule, if you do a cross section here, is 1.2 nanometers tall. Okay, so it's very, very small, and it's very sensible, because if you, for example, during the scan, if you touch it, you just move it. Okay, and okay, this is an example of some. You see here, you have a lot of those. No, there is a lot of literature produced by studying how those DNA chain behave on surfaces. No, you know, there is very like DNA origami, and there are many different research topics related to the study of the DNA. Okay, so not all the instrument is not because you have an FM that you can watch this sample. You need an FM, but you need an FM with the good sensitivity. Otherwise, this sample, I can tell you, that is very, very difficult to be observed. Okay. And yeah, all other This problematic is not only to DNA, but to, as I show you, to the fertilizer, also nanofertilizer. When you have some soft molecule, okay, small and soft, then sensitivity is a very important parameter, because otherwise you are not able to wash what you want. Again, this is another example of nanoparticles. Those are gold nanoparticles. Okay, this is a zoom. You can see here in the red markers, those nanoparticles, if you do a cross section, those are 2 nanometers in 8. Those are gold nanoparticles. Gold nanoparticles are very peculiar because if they are not protected by some lipid layer to isolate them, they try to coalesce. Just because you have to think those nanoparticles on the surface, they have their own Brownian motion, okay? They vibrate on the surface, okay? And the smaller is the size of the particle, the bigger is the amplitude of vibration. So during the measurement, if you do not use a very good and sensitive instrument, if you touch one of these, like a ball, no? If you touch it, it will start to move. And they will start to coalesce in a very high, bigger dimension size. So it's a very, very difficult to catch 2 nanometer gold nanoparticles because they are very, very reactive, okay? To do this, you need an FM, not only an FM, but an FM with an excellent sensitivity. Okay, now we'll show you, maybe I will not go too much into the detail, otherwise take too much time. Phase image, conductive image, all those, when you do FM, you do a topography. But at the same time, you can also acquire other parameters, okay? For example, this is a plastic embedded with a carbon nanotube, for example, okay? This is the topography, and this is the so-called phase image, okay? Phase image allow you to understand if the material, from the topography, you don't know if this material and this material is the same, but with the phase image, you can say, no, it's not the same material. There are 2 different materials. Again, here, you have the topography and you have the phase image. This material is different from this material, again. So with FM, you can have topography, but you can have also ancillary information that are very relevant maybe to your experiment. Again, for conductivity, here you have some quantum rings, okay? Quantum rings, those are very small. Okay, you have the topography, and then you have a conductivity map, because maybe you want to see if the center, is it more or less conductive of the surrounding, for example. Again, here some other application of conductivity. This is more physics stuff. This is more stiff. You can measure the magnetic field. I will go quick on this. This is quite nice. You can measure the electrostatic force. So if you have a sample like this, you can do the map, but you can see also how those are wired on top of silicon, conductive wire. Some of them are conductive, some of them are biased, some of them are not. You can see the difference. Okay, again here, Kelvin probe again is a ancillary technique. So you have topography and you have Kelvin mapping. From the Kelvin mapping, here in this case, the color is not a difference in 8, but the color is a difference in material, okay? Every material has a different word function, and the mapping here is a mapping of the word function, okay? This is relevant, for example, for biological application, when you want to study molecules or other things. This is very important because, for example, this is some molecules that aggregate into wires. When you drop cast this molecule on top of a surface, in this case is silicon. Those are some copper phthalocyanines, and those aggregate to form some nanowires, okay? And with the Kelvin mapping, you can see that this material is really different from the substrate, okay? And with the Kelvin probe, you can study if there is some defects, for example, you can study how uniform is the word function along your material, okay? This can be applied very easily also to if you work with transistor, but it's not the case. I don't think that any of you will work on transistors, so I skip this one. And piezo force is another technique that also I will skip it. Clearly, with FM, it's also possible to interact. I just give you an example. You can also write on your sample, but not on all your samples. In some, for example, on silicon, it's quite easy to draw lines. Those lines were made with the FM. So you can use, in this case, the FM both to read and to write. Okay, again, here some other application of lithography. I want to be a little bit more quick because, and then there are some other tools on FM like scanning tunneling microscope, SNOM, spectroscopy, electrochemical, Raman can be other tool. Okay, I just want now to present you some to focus on this SNOM tool. Okay, SNOM tool is like joining an FM with an optical microscope, but with the advantage of breaking the diffraction limit. Okay, this is done by changing some parameter. Okay, so this is the argument. So give me some time and I will show you some biological application. Okay, by now I just point out what I want to point it about the FM: resolution, accuracy, and sensitivity, plus the possibility to have additional information like that. Now I will go a little bit more in detail about SNOM and what is possible to obtain in biology. Is okay? Are you still?
Yeah, it's fine.
How many minutes do I have?
Yeah, you can go ahead another 20 minutes. Then we can go for question and answer
Okay.
session.
Okay.
You want to go for another slide?
Yeah.
Yeah, you can just close it.
No, sorry. I need to share another.
Then
okay. Can you see?
No, you're supposed to close the earlier file. You have to open Agri University Raichur, the next one. Next PDF.
New share. No, new share. Sorry. I got it. New share. This one. Share. Can you see this one? IFMS norm application. Can you see it?
Yes, fine. Perfect.
Okay. Now tell me if I go, but I cannot go to presentation mode, I think.
Yeah, you have to go with presentation mode.
No, it do not allow me to do it.
Okay.
I will continue like this. Is okay? Is it readable?
No problem.
Yeah, because I don't know how to change it.
No problem.
It's not, you see, if I go to presentation F5, it doesn't work. I think because it's because of the sharing.
Okay.
Okay, so now I will show you some IFMS norm more related on bio. Okay. So IFM is 20 years in the field, so there are so many things that you can imagine to just, I want to give you some of the research that we performed in our company. Okay, so you can see that the field that you can cover is very large: histology, cytology, biomedicine, biochemistry, genetics, molecular biology, single molecule, atomic detection, DNA, polymers, biomaterial, solar cells. So it's a very wide, very wide. So this is a little bit comparison map of different technique. Okay, so let's say I summarize the only 3 of them. Clearly there are others. So in the scale here, you have a logarithmic scale going from the millimeter to the femtometer scale. Okay, so from one side on the millimeter scale, now you have the real world, I would say, and then you go down to atomic scale. Okay, so what are the techniques that you can use to make microscopy? Microscopy, you have optical microscope. Okay, with the optical microscope, you have a limit, that is the diffraction limit. It's true that nowadays there are some optical techniques that, like FRET, others, that are able to see smaller molecule, okay? But you have to take in mind that what you are looking at is not the molecule, but is the fluorescence. So if your material with all these new optical methods and so on is not fluorescence or is not induced, you are not able to induce fluorescence, there is no way to watch it, okay? Because the diffraction limit is always there. So is a physical limitation, okay? The first instrument that was able to break the physical limitation of the diffraction limit was the electrical scanning electron microscope and the transmission electron microscope, okay? Nowadays, you can, with the TM, you can really go down in resolution, but take in mind that we are always talking about lateral resolution, okay? With those instruments, we have no Z resolution. Plus, you have the limitation that your sample needs to have a specific sample preparation. Later on, I will show you some comparison with the same kind of samples measured with those techniques. And then you have the scanning probe microscope. With the scanning probe microscope, I showed you before a little bit more in detail about atomic force microscope. Then we have the STM that is able to reach really atomic resolution. And then you have the SNOM. The SNOM is, maybe I will introduce a little bit more what is a SNOM because it's not so popular technique, okay? The SNOM is scanning near field optical microscope, okay? So what is the difference between other technique? So the SNOM is a kind of merging between the AFM, atomic force microscope, and the confocal microscope, okay? So just to give you an example, let's take on this slide, you will see this, let's say, mountain represent a cell. A living cell grow on some substrate, let's say glass, okay? So you have a glass and then you have some cell here. If you watch this cell with a confocal microscope, you will like kind of make an optically, you make an image that is only on the sides, you make a strip like this, only where the focus of your microscope is okay. So it's like make a virtual cut of your cell. So what you will see is around this area with a thickness that is anyway of this thickness here is an average of your image that is around 100, 200 nanometers, because this depends on the depth of focus of your confocal system, okay? So this part is what you observe with the confocal microscope. Plus, you have a limit of resolution that, okay, depends on the microscope, but let's say is around 300 nanometer. So you have, remember, a limitation lateral resolution, and then you have a limitation also on the Z resolution. This is with the confocal microscope. With FM is here, is in black. What you measure with FM is the black part. So you have the probe, the scanning probe, that is moving toward the sample and is following the surface, the topmost surface of your cell. So what you can map is only the black part. Okay, it's completely different from confocal microscope, and the information that you get are very, very complementary. Keep in mind, because later I will show you some example of this cell with both methods, okay? With a SNOM is like an FM plus another tool that measures the light that goes from here to here, like this part. So the SNOM is going to make a map of your system or whatever is inside, okay? Okay, maybe I skip this part because this is for a fin section, okay, but this is something different. Okay, just to give you here an example, this is a cell. So this is what you can obtain with a conventional optical microscope. It's just grow a cell on top of a glass, you know, of a cover slip. This is what you get. The contrast is very poor because the cell is made mainly of water, and there is very, very limited optical contrast. So when you do optical microscope, to enhance the resolution, or if you want to focus your attention in a peculiar part of the cell, like the nuclei or the mitochondria or whatever, you have to perform some tricks, let's say, on your cell. For example, you can make a dye labeling that can be optical labeling, or it can be fluorescence labeling. Okay, so if you change a little bit your cell, then you are able to see a little bit more structure, like in this case or in this case. But on a natural cell, it's very, very difficult to obtain some information. Okay, with so this is with the optical microscope. What you can do with the confocal microscopy? With the confocal microscopy, there is no way to see anything more. So this is the diffraction limit. Let's say the limit of this technique is 1 micron. With the confocal, you can have a resolution of 300 nanometer, but as I show here, only if you have fluorescence molecule. So in this case, you can obtain 300 nanometer resolution. In this case, you are not able to see anything. In this case, you are not able to see anything. Okay. With a SNOM, let's say FM SNOM, what you can get with a SNOM, you can have an optical resolution that is between 20 and 50 nanometer. So with a SNOM, you can see something in this case, something in this case, and something in this case. In this case, you can have not exactly the same information, but some information with a resolution that is even better than the. So I will try to stress this part, okay? So I don't know if you can follow this this structure, no? The idea is how to go down the micrometer scale. So I'm not interested in watching big stuff, okay? We want to watch whatever is in the nano scale. It means below 1 micron size, okay? And this norm can help us quite a lot, okay? Maybe I can skip this one. It's not a biological application, okay? This one, let me see, will come later. Okay, this is an example of something that we published in the past. This is the study of those small structures that are on the, not in the center of the cell. So this is cell, and we wanted to study is the filament structure on the, let's say, outer part of the cell, okay? Okay. So this is a topography. This is exactly what you can obtain also with FM. Okay. So this image is 30 by 30 micron, and you can zoom in with the FM. So this is what you can get with FM. You see very, very small structures here. Okay. Those are 10 nanometer in 8. Okay. So this structure is not colored, okay? This is a natural cell. It is a cell that we didn't made any alteration to the cell structure. So with the FM, you mentioning the topography, you can really go down to see those very narrow structures that are not visible with any other technique. By comparison, I put here a SEM image, scanning electron microscope image. You can see here, okay? This is the part of the cell that we want to study, okay? With a scanning electron microscope image, you are not able to see anything of this. Why? Because to make this SEM image, you have to evaporate on top of your cell some gold or carbon to make it conductive, because the electron microscope requires that the sample is conductive. Okay, you agree? So how much is this amount of gold that you put on top? So a lot of biologists do not think about that. But what you put on top is around between 10 and 20 nanometers of gold. So it's like putting a carpet of 10, 20 nanometer on top of your cell. That's why those small structures are not visible anymore, because they are smaller than the gold or the carbon or the coating that you put on top of your cell. Okay, I don't know if it was clear enough. So this is what you get with SEM. No details on the outer part, and with FM you have a lot of details on the outer part. Okay, again here to stress, this is an optical image of the same, this is a topography obtained with this number, with FM will be the same. Okay, so you are able to see all these structures that are not clearly visible also of the optical microscope, because they are very faint. The optical contrast is very poor. Okay, there is, as I said here, there is no labeling with a fluorescence anything. It's a natural cell, and this is what you get. And then from here you can zoom and you can have this topography. Okay, so this is what you can get with FM. With the SNOM, as I said before, you can make also optical image in reflection and transmission, and you see what you get here. Now you have some contrast also. You can measure the topography, plus you have some optical contrast on a cell like this that on the conventional optical microscope do not exhibit any contrast. Plus, if you want, you can induce some more evident contrast. Again, here we have a cell, and this cell, this is the topography. Okay, in this case we stained with some dye. Okay, so it's like painting the molecule. So in this case you want to see this microtubula here. So this dye is as a special link that goes to be attached exactly on some tubular structure that we expect to measure. Okay, so this is the topography, and this is the color, I would say, with a scale that is below the diffraction limit. Okay, so this is a combination, again, I repeat, of FM plus optical imaging and nanoscale that is called SNOM, scanner near field optical microscope. So this is a conventional FM and this is SNOM. We published this stuff, was quite nice. Again, here is a you can merge the two information to create a 3D colored map. In this case, the color is a real color. Okay, I don't know how much time I left. I don't want to go too much. It's also possible to watch film section. Okay, this example is a similar. This is a comparison between FM and SNOM with a TM, transmission electron microscope. But I want to skip this part because otherwise I'm too long. This is another case study that we performed with the use of FM and SNOM. So this is a part of the cell. This is the nuclei. You can see it here. This is the topography you can get with the cell. So this nuclei is contaminated by some asbestos fibrilla. You know about asbestos, no? Asbestos is a very dangerous system that can produce some very bad illness, no? And so the aim of this study was to understand if the small asbestos fibrilla, okay, was entering into the cell, and if entering into the cell or if entering into the nuclei. Okay, so we have a cell, we have the asbestos fibrilla here. You can see it from the topography. From here, it's difficult to understand if this fibrilla is you have a cell, you don't know if the fibrilla is here or is here, okay? And with the help of the SNOM, we were able to see that this fibrilla is is below the surface, but not in the middle of the cell, but just only few nanometers below the surface. Just making a comparison between the transmission and the reflection image. So before we are talking about some dye, okay. Sorry, this photo is not loaded. Okay, we'll go directly to the next. Okay, again, here is a comparison, not is a comparison between FM and confocal microscopy. Okay, so this is an FM image of a cell. This is a 3D image. As I said before, white means tall. This is the tallest part, and this is going down. This is a very, very shallow part of the sample. Okay, this is what the image that you can get with the confocal microscopy is a. This cell was treated with some fluorescence dye, and it's possible to do the fluorescence mapping. Okay, so the fluorescence mapping is a slide of a cell. This is what you get. You have some very bright part here and some, let's say, less bright part here. And this is the image that we obtained with the SNOM. They look similar, but in reality, they are completely different. Because with the SNOM, we can see the bright part here again. But with the SNOM, we can also see this very shallow part here. See this part here? We can see some fluorescence contrast. And with the confocal microscope, you don't see anything. You don't see anything because you are not in the same range of focus. You remember with the confocal, you have a depth of focus between 100 to 200 nanometer, okay? But in this case, those fibrilla, you can measure it here. This is FM and this is SNOM. With FM, you can see that those are very narrow. Those are around 10 nanometers. So you will lose this information in the confocal microscopy. But in the fluorescence FM SNOM image, you can watch them and see them. So if you are dyeing, you are putting some dye on your cell and you do perform only confocal microscopy, you can see that all the dye is going on this structure. But this is not real. In reality, this is the real situation. Okay. So every technique is important by its own, but in all the study, it's always important to use different technique to overcome the limitation. Also, the FM have a lot of limitation, like confocal, but to be sure of what you are measuring, you need to use multiple technique. This is an example on bacteria. Maybe I didn't have time now to show you, but in the current stage, we are working a lot with the bacteria because bacteria are small, but not too small, big, but not too big, okay? And bacteria are very nasty stuff. With FM, it's very easy to watch them, but they look, all of them look the same, okay? All of them look like balls with the FM and with the topography. But with the SNOM, it's possible, for example, in this case, performing different images, try to understand, to explore what is the inner part of a single bacteria, okay? You could perform Raman, fluorescence, spectroscopic measurement. There is a lot of can be done. And this is actually, I will not show you now, but this is maybe next time what I will show you, because this is a very strong field of interest in this case for us. So we are performing a lot of study on bacteria, trying not only to see the shell of the bacteria, but to explore with the FM, with the SNOM, and with the Raman, the inner part of the bacteria. We did the same, for example, with some human spermatozoa. Here you see the topography, and we recently also published some new papers. Okay, so this is a 3D of FM obtained with FM. It's quite nice, but it's okay. But we want to study the tail of this spermatozoa and to see the inner part, okay, or the tail. With FM, you can watch the tail, but in this case, with the SNOM, we were able to put in evidence some structure like this corona and these small clusters, some structure that we were able to associate with a well-performing spermatozoa, or let's say not well-performing spermatozoa. This is very, very relevant. For example, we are performing this study with a group in Trieste that is very active in the in vitro fertilization for humans. No? And this is my last slide. So I know that I showed a lot of things. I'm not sure that the feedback is very difficult to get feedback, but I want to leave some, a lot of other images if you want. Maybe also if Babu has some comment, did I forget to tell you something, or if you have any specific question, now is your turn. Thank you
Suresh,
for the
yeah, thank
attention.
you, Proto. Let us see if Suresh is having any comments. Suresh, can you add something? You can unmute yourself. Can you unmute yourself?
So more than me, I would like to invite some question from panel so that Prato can clarify.
Yeah. Sure. So we can have interaction later on, Suresh. So let us have the question answer session for this afternoon session. Is it okay, Prato?
Yeah. I'm here.
Thank you very much, Stefano, so for your wonderful explanation in the afternoon session, especially in the afternoon session for us. Probably your time may be a morning, I believe.
My time is almost in half an hour will be lunchtime, so it's okay.
Okay, yeah, lunchtime. So it is afternoon time for us. So the guys may have, but you have made them very active and you put a probe on their head.
Yeah, it's.
So
I
made them.
hope that maybe someone has some question, because
Definitely.
without the feedback of the faces, it's difficult to understand if.
Correct. No, definitely.
And this field is not exactly my field, so I didn't want to. I wanted to use a little bit more images rather than formulas, because maybe they are too boring. Okay.
Yeah.
I
So
don't know if people appreciate it or not. I hope so.
Can you close this presentation, Prato, if you don't mind?
Yeah. I try to. If stop share, like.
Yeah, stop share. Yeah. Thank you. Perfect. Yeah, it is open for the question and answer session to the Prato. You can type chatting in the question and answer chat box. Even it is both YouTube as well as in the Zoom chat box. It is open, so you can start chatting. Yeah. Prato, shall we start the interaction?
Yes.
Yeah.
Yes, please.
How good is the AFM compared to other electron microscope?
My FM is. I try to a little bit more genetic. If you want to be more specific, I think that what we can offer is a very nice resolution. The chapters that I show you, okay? As a resolution point of view, it's clear that you don't have the perfect machine, okay? Because some machine maybe is better in resolution, some other is better to work with liquid, some other is better to work with other things. Our system, I think, is very strong in the 3-point resolution. Okay, very. Let's say around the world there are around about 10 different kind of FM, and I think that as a resolution, we maybe with another one we are on the top. Okay. So what are the 3 points where we are really strong? Is resolution, accuracy, and the sensitivity. Okay, I would say that some of our competitors can have similar performances. Okay, but definitely not with the same price. No, I don't want to comment about my competitors. No, but it's true that some of the measurement that we do, all the measurement that I show you, a part of the SNOM, in the SNOM field, I think we are on the top. Okay. Because SNOM is a quite complicated technique, and not many companies are delivering SNOM. So I think only 1 or 2 companies can do something similar, but not, I think, as we do. with the snow. But on the FM side, what we try to propose is something that others can achieve, but with not with our price level. That's why one of the reasons why we like a lot to work in India, because in India there are very good scientists that can understand very well the quality of the instrument, but is a little bit more like Italy, no? People like to want the good stuff, but with a reasonable price.
Yes, yes, yes.
And this is why we, in this moment, we are performing quite well in India, and we are investing a lot because we have good feedback, good researcher, and I think that our product is very well in fit with this market.
Yeah. So what is the difference between AFM and Raman?
It's completely different, clearly. FM is a topographic technique. It gives you a 3D reconstruction of your surface, okay? Raman is a little bit, has the advantage of having a chemical sensitivity, okay? I didn't speak about Raman, but with Raman, I would say is an ancillary technique that many images that I show you, in some images, you can expect to have Raman contrast, but not all material exhibit Raman contrast. Some material have a very faint Raman constant, some material have a stronger Raman contrast. A part of that, Raman is an optical technique, okay? So in theory, it's possible to overcome the diffraction limit with Raman. No? There are some techniques like, in particular, tears, no? Tip enhanced Raman scattering, but it's a very, very complex technique that we are able to perform. But we do not propose as a, let's say, turn-on. Is a very, very delicate technique, and is suitable only for a certain amount of material, not for all material. So before I know that TERS, for example, is quite popular technique, but there is so much to be done with FM and with the Raman itself before to join them, okay? It's possible to join them, but this, I think, is recommended only for groups that are, first you have to become expert in FM and in Raman, then you can try to join them. Technically, it's possible, but from the, you know, it's like to have a good FM image, in one day you have a lot of samples, no? You can, I mean, it's not like a camera, no? In optical microscope, to take a good image, it takes FM, no, 1 minute, 2 minutes. With FM, it requires 1 hour, 2 hours to have a good image, maybe sometime 1 day, okay? And for the scanning Raman, for example, if you want not high resolution Raman, but the scanning Raman, to have a good mapping, it requires 1 day, maybe. If you want to do tip enhanced Raman, the complication, you know, is
Yes.
sometimes you see very nice picture, but maybe it's a job of 2 or 3 months. So,
Yeah.
so it's possible. There are completely different techniques that can be merged, but depends on what is your goal,
Okay.
essentially. Okay.
Is it more
And,
sensitive?
normally, people that is doing TERS have more than one system. No, maybe they have one FM for preliminary measurement, then have dedicated machine to the other part that is very important for the FM is the ability to use the FM. Because the FM, it can be any kind of FM, but you need a good researcher that is able to make it run properly. Okay, this is a part also that our company take care a lot. Okay, we are not working all around the world. No, we are, for example, in India, we have Suresh Babu, we have other people that is dedicated not only to sell, let's say, an FM, but also to maintain it and to assist the customer if in the future needs. No, you know that we are always open to have feedback to help, because to train a proper student to make good images it takes some time. Okay, so the quality of a FM paper is 50% by the machine and 50% by the user, I would say.
Okay. Is it more sensitivity of as compared to the XPS, Prato?
XPS is a completely different technique. First of all, XPS require vacuum, okay?
Yes.
Plus, XPS is very sensitive to the chemical composition, okay, of the system. But XPS by itself is a technique that has a lateral resolution of about 1 micron. Because when you do XPS, you have your X-ray come and generate a lot of secondary electron. And this secondary electron produces like cloud into your sample. No? So it's very difficult to enhance the resolution of XPS below 1 micron. There are in the synchrotron some special beam lines dedicated to this. It's possible to do XPS in the nanoscale, no? Because I mean, XPS is very, very well used above 1 micron. This okay, but if you go below 1 micron, then okay, you need a very special beamline and a special synchrotron to do that. It's not is a completely different. XPS is they work the chemical composition by atoms, but is not suitable to do a very nice imaging for high resolution.
Yeah. So
By itself.
what are the important applications of Raman spectroscopy?
Raman is used in so many fields that first the only things of Raman is that not all the molecules are Raman active. Okay, there's a problem of selection rules in physics, so not all material is Raman active.
Correct.
So it's not Raman. For some material is very powerful. For some material is useless. So it's not like the perfect solution for all the problem. Is one solution for some problem. It's nice to have in a laboratory. Clearly, in a laboratory, it will be nice to have a SEM, IFM, Raman, everything, because any material is there is no recipe, general recipe. For some material, is quite. For some material, can be a little bit more annoying. Okay.
Yeah. So what is the difference between AFM and SEM?
I tried to show you before the AFM. When you make the topography, you are not touching your sample.
Correct.
With ASM, you are bombarding your sample with electrons. Okay. In fact, one typical stuff of scanning electron microscope is the radiation damage. When you zoom in a lot, into an area, no, you will see that this area change a little bit. So if you have a metal, maybe it's not so important. But if you have soft material, then it's important. The other key point is that with FM, the sample preparation is very simple. You just put a drop of your material in some sample and so on, okay? But with SEM, you have this problem of metallization. If your sample is not very well conductive, you have to metallize it. Even let's say if it's conductive and you do not metallize it, if the material is very soft, the energy, because the energy that becomes that comes down with a standard SEM is a kilovolt. So you have high energy electrons coming into your sample that in general change your and the other key point is that with the SEM you are able to see lateral resolution. You have very nice zoom capability. Okay, you can zoom very fast, but then you watch only the lateral resolution. You are not able to measure the how tall is one molecule or one sample. So this is the main difference. They are anyway complementary. For some sample, it's better to use the SEM from, let's say, but in the nanoscale in general, the FM is a little bit more complicated, maybe, because it's newer and is not so easy to understand why it can be used, why should you use it. So, but once you get familiar what is the potential achievement that you can get by your FM, then is definitely more flexible.
Yeah. Whether conductivity is required in AFM to the samples as compared to the ACM?
Nothing. Also, a lot of images that I show you were done on glass, so
Yes.
do not require conductive sample.
Okay. Can we do the biological samples for by using AFM, live samples?
Yeah, I show you that you can use it. Most of the images that I show you were done on dry sample. It's possible also to do it on wet sample. The problem of wet sample, let's think about a cell. If you dry a cell, the cell, let's say, is a little bit more stable. When you work in a dry sample, all stuff can move around. This is the problem. So if you have nanoparticles, if you watch it on a wet sample, they do not stick on the surface. So since to get an FM image, you need at least 10, 20 minutes, let's say 10 minutes, 15, whatever. No? During this period, the molecule needs, what you want to watch needs to be stable. And this is not possible if in some material, even cells that are quite big, when they are in liquid, they move because they are alive. No?
Yes.
It's like, just an example, if you want to have an haircut, no? You need to stay there in the chair, and then the barber shop, no, cut you. Is a little bit more difficult if you ask for a haircut while you are running. Okay.
Yes.
It's in theory possible, more difficult, but I don't know if you get my example.
Correct.
It's possible, but most of the time it's easier to do it in a dry sample. This is definitely the answer.
Yeah. So what is the methodology for sample preparation for biological materials?
Yeah, this is the key. There is no general recipe. Okay. That's why we do a lot of research. Okay. Because for some sample, sometimes the sample preparation is very, very tricky. So let's say in general, for any sample, you have to find out which one is the best sample preparation. If you remember, for example, the image of DNA on mica, you remember it? Okay.
Yeah.
I know personally the student that invented that method, no? But for 10 years, people were just trying to watch DNA without any success. Nothing. They tried, they say, because theoretically it was possible to watch it, but practically nobody was really able to watch it until this student in New Mexico, no, find a recipe to properly deposit it, no, because you should put the DNA molecule. First of all, should not move, otherwise you don't see it. So it needs to be fixed on the surface, but it needs to be very well aligned. Otherwise, it's make like spaghetti, no? So is used. So after this work that was done, I think in 1998, 96, something like that, with that recipe, once this student invented this recipe, then a lot of other people start to do DNA study with FM and so on. So sometimes really, if you are the first one watching some samples, maybe it maybe is a job of 1 day or 5 minutes. Sometimes can be a little bit tougher. Sometimes a sample, the easiest way to prepare a sample is to take something very flat, silicon, mica, HOPG, or glass also, even if glass is not so flat, no? To put some solvent, let the solvent to evaporate and try to see what is left. Okay, for example, with nanoparticle, I can share with all of you some trick that we use. Sometimes we take a glass, we put a drop, just a small drop, not a big drop, on the center. The drop will dry, and you will see the drop, but the nanoparticle have some diffusion efficiency. So usually when we explore for nanoparticle, we do not go into the drop, but we go out of the border of the drop, because on the drop, some nanoparticle will spread around. And that's the best way to find isolated nanoparticle, for example. But so this is a trick, but there can be others. Depends a lot on the kind of sample that you want to explore.
Yeah. So what is the energy requirement of AFM, Dr. Peter?
Energy, what do you mean?
So probably the sample analysis energy requirement, because as in case of SEM, we require more energy, but as compared to the.
No, but there is no energy involved in the FM. Okay, FM is a technique that do not involve any particular needs of.
Yeah. So the question may be, which technique is better, AFM or STM?
It really depends. If you want to watch single atoms, then you need to watch STM. But STM is better to be used, is a more a material science method, because STM is good to see single atoms, okay? But to see single atoms, they need to be arranged in some specific pattern. So it needs to be a crystal, a pure crystal. So to watch it a pure crystal, you need to work in ultra high vacuum. So it's a completely different system, because otherwise, when you work in ambient, your sample get oxidized. I showed you before the gallium arsenide sample, no? You're watching the steps, monatomic steps, but what you are really watching is the oxide that grows on top of the steps. Because in ambient, STM is a more UHV technique, let's say, no? More resolution, more in UHV. Is a similar, you can also do, we do a lot in chemistry, for example, when we study molecules like phthalocyanines, other kind of molecule, then is also put carbon nanotube, all this kind of things is also possible to use STM in ambient, but has a little bit more limitation than FM. Because for the STM, then you need to have conductive sample, because the probe is a tip that uses the tunneling effect. The tunneling effect needs conductive samples.
Okay. So what is the resolution of AFM, Preto?
The resolution really depends, as I say, depends on Z resolution. We were able to demonstrate 40 picometer resolution, our FM, okay? Some other FM have 1 nanometer resolution, or even worse, in Z. Okay. Lateral resolution depends on the size of the tip, okay? The standard tip has a radius of curvature of about 5-10 nanometers. So you can expect the resolution that is around that level, okay? But it's possible to buy special tips with the nano whiskers that has a resolution higher. Let's say the higher is the price of the tip, the higher is the resolution. Yeah. So the limitation is a little bit about the tip itself rather than on the machine. Okay, lateral resolution. Okay. Z resolution is important. Then depend on the machine.
Okay. So I have completed all the question answers through chat box as well as in the YouTube box. So if any queries or any clarifications required from the Preto, so it is the most welcome. I will pass the chat, your queries to the Preto or Suresh for your clarification, and same thing will be updated you. So anything to be added by Suresh before? Yeah, you can unmute yourself. You can add something if you want.
Yes, it was a very good presentation. I hope most of the scientific fraternity, it was much useful for them, because especially when it comes to AFM, so people ask more on sample preparation and application. So I hope this session clarifies most of the doubts faculty is having.
Okay. So thank you, Preto. Anybody wants to talk to Preto, you can raise your hand so that I can connect to Preto also. Anybody wants to talk to Preto to clarify something, any doubts? Any doubts if you have any clarifications with the Preto so that I can connect with the Preto? No problem. Or 1 minute. Okay. Yeah. So
if someone want to have some specific question, maybe some sample about preparation, you can feel free to contact me or Suresh Babu, and we will try to do our best to be helpful,
Yeah.
even later on. Okay.
Yeah. Suresh, can you mention the lab facility at IASC, if you
Yeah,
don't?
yeah. Coming to AP research activity in India, we have a very exclusive dedicated AFM facility at Indian Institute of Science, Bangalore. So it is a dedicated facility for various AFM applications. Whoever interested to see the system and wanted to do some kind of testing, so you are welcome, so that we can show you how the AFM works, and what all things we can do on AFM, we can able to show you in a complete way. So I would like to invite most of the scientific faculty here, over here. So if you are interested in some particular application, so they can visit us and they can discuss with us, sir.
Yeah. So thank you very much, Suresh, and thank you very much, Proto, for your wonderful session. So on behalf of the University of Agriculture Sciences, Center for Nanotechnology, and my College of Agriculture Engineering, I wholeheartedly thank you, Proto, for your wonderful presentation, that too in the afternoon session, and made the day a grand success, I can say. And nice information which you have given from the AFM in the initial principle, then what are the different modes of the AFM, and how they are using in the different field of agriculture. So thank you very much for your time,
Welcome. It's a
presentation, and
pleasure.
thank you. Thank you very much. Jai Hind.
A pleasure. Thank
Thank
you.
you. Thank you.
Bye
Thank you.
Bye.
bye.
Thank you, Suresh.
Thank you, sir.
So
Thank you. Welcome.
yeah.
Thank you.
So
Bye bye.
bye. Take care.
Bye. Bye.
Pito, take care, because it has been most affected places in the earlier days. How was now? How was the COVID situation in your place?
Here in my place is quite safe. It's not a problem, but people start to be a little bit more worried because every day we have bad news. So
Yeah.
I don't know.
Okay.
We have to
Take care.
cross finger both sides.
Yeah.
This
Yeah.
is this is a real challenge. So for everybody, use the mask, keep distance, and let's hope that we get a good vaccine.
Correct. Correct.
Because this
Yeah.
is,
Yeah.
meantime, everybody be careful. Okay.
Yes. 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 That's what our
And
slogan.
as soon as this stuff will go over, maybe we meet each other personally. Okay, that will be
Definitely.
much
Definitely.
better.
Definitely. We'll meet
Good
soon.
luck to everybody.
Yeah. Thank you. Thank you, Preto, for your wonderful session and nice presentation on this day.
Okay.
Thank you. Thank
Bye
you very
bye.
much. Yeah. Bye.
Bye.
Thank you, sir. Bye.
Take care. Bye.
Bye.
So this is the information to the audience, our delegates for the tomorrow session. We have two sessions tomorrow. So Dr. Deepa Bhagat, she is a principal scientist, ICR NBR Bangalore. She is going to deliver a lecture on nanogels and nanosensors for agricultural pest management in the morning session. So please join at 10:50 a.m. in the morning. And in the afternoon session, we have a Dr. Alois Daniel. He is going to explain about the advancement in SEM, scanning electron microscope, and its applications in the afternoon. He is from Kalgis, so he is going to explain about uh, uh, what are the applications of the SEM, scanning electron microscope. So don't miss these two wonderful presentations in the morning as well as the afternoon. So thank you very much for your participation and presence in the afternoon, and made the day a grand success. Thank you very much, and stay home, be safe. Jai Hind. Thank you.